This is a question from GATE 2015 from Chemical Engineering, question number 57. A catalyst slab of half thickness L, the width and length of the slab are very greater than L, is used to conduct the first order reaction A giving B. At 450 Kelvin, the Thiele modulus of the system is 0.5. The activation energy for the first order rate constant is 100 kJ per mole. The effective diffusivity of the reactant in the slab can be assumed to be independent of the temperature, and external mass transfer resistance can be neglected. If the temperature of the reaction is increased to 470 Kelvin, then the effectiveness factor at 470 Kelvin up to 2 decimal places will be dash. The value of universal gas constant is equal to 8.314 joule per mole per Kelvin. So this is a question based on internal diffusion from Chemical Reaction Engineering 2, and the reference NPTEL lecture can be found in lecture 10, Intra-particle diffusion, Thiele modulus and effectiveness factor part 1, Chemical Reaction Engineering 2 by Professor Sanjay M. Mahajani, Professor Ganesh A. Vishwanathan and Professor A. K. Suresh from Department of Chemical Engineering, IIT Bombay. So, in this question, our main objective is to find the internal effectiveness factor, which you can represent as eta at 470 Kelvin. And this internal effectiveness factor can be found by using the formula tan H phi by phi. And this phi is basically the Thiele modulus, which is equal to L into root of K by dE. And since the effectiveness factor needs to be found at 470 Kelvin, you need to find the Thiele modulus at 470 Kelvin. Or in other words, this K, reaction rate constant K, is also at 470 Kelvin. So let us write down the data they have given us in this question. So the first data they have given that Thiele modulus is equal to 0.5. Let's say this is Thiele modulus for case 1. So Thiele modulus phi 1 is equal to 0.5. Other data they have given is that the activation energy EA is equal to 100 kilojoule per mole. And they have also mentioned that the effective diffusivity of the reactant in the slab can be assumed to be independent of the temperature, and external mass transfer resistance can be neglected as well. So based on all these data, let us see how we can find the internal effectiveness factor at 470 Kelvin. So let us first start by using our Arrhenius equation. So by Arrhenius equation, ln K2 by K1 is equal to E by R into 1 by T1 minus 1 by T2. So here EA is given as 100 kilojoule per mole. This is basically 100 into 10 raised to 3 joule per mole. Then T1 is basically 450 Kelvin and T2 is 470 Kelvin. And the universal gas constant R is also given as 8.314 joule per mole per Kelvin. So just substituting these values in the Arrhenius equation, we can get ln K2 by K1 is equal to EA, that is 100 into 10 raised to 3 by R 8.314 into 1 by T1 minus 1 by T2, that is 1 by 450 Kelvin minus 1 by 470 Kelvin. So solving this, we can solving this and taking the exponential, we can get K2 by K1 is equal to 3.118. So let us take this as equation 1. Now for our next step, we need to use the concept of Thiele modulus. And Thiele modulus 5 is given as L into root of K by dE, where dE is the diffusivity or mass diffusivity, K is your reaction rate constant, and L is the catalyst slab length. So phi 1 will be L1 root of K1 by dE1, and this phi 1 is the case 1 at 450 Kelvin, and phi 2 will be L2 root of K2 by dE2, and this will be for 470 Kelvin. So in the question, they have given that phi 1 at 450 Kelvin is 0.5. So using these, we need to find phi 2 at 470 Kelvin. Now, other data that they have given is that L is constant because the length does not change with temperature. So L1 is equal to L2. Also, they have given that your mass diffusivity is independent of temperature. That means dE1 is equal to dE2. So if we write phi 1 by phi 2, on the right hand side we will get L1 root of K1 by dE1 by L2 root of K2 by dE2. So because L1 is equal to L2, we can cancel out L1 and L2. dE1 is equal to dE2 because the mass diffusivity is independent of the temperature. So we can cancel out dE1 and dE2. So this will lead us to phi 1 by phi 2 is equal to root of K1 by K2. So let us take this as equation 2. So we have two equations here. The first equation being K1 by K2 is equal to 1 by 3.118, because here it is K2 by K1, which is 3.118. So K1 by K2 will be 1 by 3.118, and also we have phi 1 by phi 2 is equal to root of K1 by K2. Also we have phi 1 as 0.5. So substituting all these into this equation 2, we'll get 0.5 by phi 2 is equal to root of 1 by 3.118, because phi 1 is 0.5 and K1 by K2 is 1 by 3.118. And if we solve this, we'll get phi 2 as 0.885. So this is our Thiele modulus, at 470 Kelvin. Now using this, we can find the internal effectiveness factor at 470 Kelvin. So our internal effectiveness factor eta will be equal to tan h phi by phi, and that is basically tan h 0.885 by 0.885, and this will be approximately equal to 0.885. So rounding off this to two decimal places, this will be approximately 0.89. So our internal effectiveness factor up to two decimal places will be 0.89.